Good afternoon, ladies and gentlemen. Dr. John Belkowitz here, Intelligent Concrete. We're here to talk about, we get this question a lot, so this is kind of like a tech review as well as a Q&A day, I guess. But anyway, it goes back to concrete beams and slabs when they're being put into a flexural state. And this is one of my favorite little dioramas or models that we have here. This is supposed to be your beam. And if we put the beam in a bending moment, it starts to smile. And the bottom of that beam is in tension while the top is in compression. So traditionally what we do to reinforce that concrete beam or that slab is put our reinforcing steel in the bottommost portion of our beam, and not all the way at the bottom, but where we show that it does its best job to support that tensile load. As it turns out, that's not really the best place. Now, when we're talking about a beam in flex, the assumption is all the tensile load is going on in this bottom half portion of the beam. Now, what we've done for you is drawn a contour plot. Ding! So, putting the steel reinforcement in the bottom portion of the beam is a quality method, and it does yield good results. I mean, we've built structures throughout time based off of that concept. That being said, there are better ways of doing it. As you saw in that contour plot, ding! As you saw in that contour plot, the stress distribution is actually going through the entire beam. So, especially when you're using wire mesh in structural slabs, putting the steel at the bottom, especially if you're not using frogs or spacers or chairs, and your steel mesh goes to the bottom, you're not going to get the efficacy out of it that was intended. The design of using that steel to reinforce the tensile load. By using steel fibers, and I think we've got some nice photos or close-ups of it. What's it called? B-roll. B-roll? We've got some nice B-roll. I'm using the technical jargon. The great thing about using fibers, hooked end are my favorite, and there's these different types. To use sizes, and they have, as the name implies, it's a steel fiber with a hook at the end of it to help with that composite nature bonding to the concrete. But you get a universal distribution of fibers throughout that might not have the same diameter as the wire mesh, but because they're universally dispersed, they're going to have a better chance to absorb the energy coming from that contour plot than something that's just dropped to the bottom of the slab or the beam. And there are different types of fibers that are designed. It's not only the hooked end, but it's also the steel fibers. But the impetus of using the steel fibers over cellulose and macrosynthetic or synthetic fibers is that the steel fibers actually have that F's of Y, that yield strength to absorb those tensile loads that would cause catastrophic failure. And the great thing about it is, opposed to using a mesh that can drop to the bottom of the slab, the steel fibers, like I said before, are going to be universally dispersed, so it gives you that factor of safety, that insurance policy that you're going to get that absorption and that protection from those catastrophic loads. And we're actually writing an article about this, and it's really going to focus on using fibers per steel mesh, and we go into a lot of the theory on what the zone of influence is for a steel fiber versus a steel mesh, and it's based on not only its geometry, but it's also its shape and the size of it, as well as the material properties. So stay tuned for that. Hope you had fun today talking about this awesome concept with steel fibers versus mesh. If you have any questions, any concerns, shoot them below or send us a direct message. Don't forget to like and subscribe. Go concrete, beat asphalt.